context injection, interceptor, and notification listener. Listing 12.17. Interceptor that rejects events until the context is initialized. Did you notice how you apply our previous suggestion and extend abstract intercepting message processor to have less code to write in the interceptor? Because a custom interceptor configuration element doesn't expose an ID that you could use to register it with Mule's notifications infrastructure, you have to perform this registration programmatically. This interceptor is configured using the custom interceptor element, as you saw in the previous section. Again, notice how there's no ID attribute that could allow you to register it as a notification listener by configuration. Custom processor. Class equals com.prancingdonkey.interceptor.broker not ready interceptor. Therefore, the notification configuration related to this interceptor consists only of the activation of the context family of events. Notifications. Notification event equals context / notifications. More notification goodness. Mule's notification framework offers advanced features. Associating a custom subinterface of org.mule.api.context.notification.server notification listener with an existing event family. Disabling standard listeners to receive events from the family they naturally listen to, for example, preventing all implementations of org.mule.api.context.notification.routing notification listener from receiving routing events. Creating custom notifications, as represented in Figure 12.6, listening to them, and broadcasting them programmatically. Mule's extensive notification framework can help you graft advanced event-driven behavior to your applications. But not everything that flows in Mule is as ephemeral as events, some information needs to be persisted. Let's now discover how Mule manages its own persistence needs. 12.3.4. Configuring Mule data persistence. Have you ever wondered where the messages in a persistent VM queue are stored? Or where Mule keeps track of unique IDs in an idempotent message filter? Indeed, Mule has to manage state for many of the moving parts that you can use in a configuration. This state is managed independent of whatever transports or modules you're using in your configuration. It's persisted with an internal framework called the object store. It's important to know about it so that you can understand where Mule's state data is going and how to configure and customize its persistence. Take a look at the configuration shown in listing 12.18, which consists of a bridge that receives messages on a VM channel, filters out the ones it has already processed, and attempts dispatching to a proxied service until successful. Listing 12.18. A flow that relies heavily on Mule's internal object store. Spring bin name equals until successful store. Class equals org.mule.util.store.partitioned in memory object store. VM connector name equals VM connector. VM queue profile. Default persistent queue store. /VM queue profile. /VM connector. Flow name equals idempotent bridge. VM inbound endpoint path equals ib.in. Idempotent message filter. Simple text file store name equals zip.idem. /idempotent message filter. Until successful object store ref equals until successful store. Outbound endpoint ref equals proxied service. /until successful. /flow. The idempotent bridge flow shown in this example relies on Mule's internal persistence to store the state of 3 of its moving parts. The persistent inbound VM queue uses the default persistent queue store to store the messages pending delivery. The idempotent filter uses a simple text file store named ib.idem to store the unique identifier of each message it processed. The until successful routing message processor uses a Spring configured object store to accumulate messages pending outbound dispatch. At first glance, it seems that these 3 configuration mechanisms are quite different, but they all rely on the same internal object store API. Figure 12.7 shows the hierarchy of interfaces that compose Mule's internal object store API. There are many classes that implement these interfaces, and numerous XML configuration elements that allow for their configuration. This figure only lists, in notes, the ones that are in use in listing 12.18. Figure 12.7. The interfaces of the Object Store API and some elements or classes using them. By default, the file-based persistent object stores save data under the Mule work directory, 8, in a structure of subdirectories that's created on the fly. For the previous example, you'd find these subdirectories, /qstore/ib.in and /objectstore/ib.idem.dat, respectively used for the data of the persistent queue and the idempotent filter. 8. Typically a directory named Mule located at the root of the execution directory. Database persistence. If you want to use a database to persist Mule data, look no further than the org.mule.transport.jdbc.store.jdbc object store, an object store that, behind the scenes, uses the standard JDBC transport of Mule. It works by using custom queries that you craft to provide the basic CRUD operations needed by the object store. Prancing Donkey has developed a great deal of experience with Ahash, so they've decided to create a custom object store implementation that uses Ahash as its backend storage. They'll implement it as an org.mule.api.store.listable object store, which will cover the needs of until successful and idempotent message filter, and will use the org.mule.util.store.qstore adapter to adapt it as an org.mule.api.store.qstore so it can be used for VM queue persistence. They'll also extend org.mule.util.store.abstract object store to have a big part of the implementation done for them already. Listing 12.19 shows the implementation in all its gory glory. There's not much to say about it except that it delegates all operations to the Ahash instance that's been provided by injection. There's some general impedance mismatch between the Object Store API and standard caches. For example, the Object Store API expects exceptions to be thrown in many circumstances in which a typical cache wouldn't report any problem, like when overriding a key. The mismatch is visible in the doRemove method, in which you jump through hoops to return the last value of a key you delete from the store. 9. This implementation is far from perfect. The value may have changed between the retrieve and remove operations. Listing 12.19. An Ahash-backed listable object store. Public Class A cache object store. It extends serializable. Extends abstract object store. It implements listable object store. It private Ahash cache. Public void set cache. Final Ahash cache. This dot cache equals cache. Public boolean is persistent. Return cache.get cache configuration is disk persistent. Public void open throws object store exception. //anoop. Public void close throws object store exception. //anoop. At suppress warnings unchecked. Public list serializable all keys. Throws object store exception. Return cache.get keys. At override. Protected boolean do contains serializable key. Throws object store exception. Return cache.is key and cache key. At override. Protected void do store serializable key, t value. Throws object store exception. Cache.put new element key, value. At suppress warnings unchecked. At override. Protected t do retrieve serializable key. Throws object store exception. Element equals cache.get key. Return element equals null. Null, t, element.get value. At override. Protected t do remove serializable key. Throws object store exception. T removed value equals do retrieve key. If removed value equals null. Throw new object does not exist exception. Boolean removed equals cache.remove key. If, exclamation mark removed. Throw new object does not exist exception. Return removed value. With this implementation in hand, you can now reconfigure the previous example in such a way that different hash caches are used for each of the configuration elements that need persistence. Listing 12.20 shows this new configuration. The configuration of each individual hash cache, VM cache, idempotent cache, and until successful A cache, isn't shown. Spring or cache zone configuration mechanisms could be used for that. Remember how we mentioned that you would use a QStore adapter to fit an hash object store into a configuration element that takes a QStore? You can see it done in the configuration of the Spring bin named VM QStore. Listing 12.20. Using custom hash-backed persistence. Spring beans. Spring bin name equals VM store. Class equals com.prancingdonkey.objectstore.a cache object store. pcache ref equals VM cache. Spring bin name equals VMQ store. Class equals org.mule.util.store.qstore adapter. CStore ref equals VM store. Spring bin name equals idempotent store. Class equals com.prancingdonkey.objectstore.a cache object store. pcache ref equals idempotent cache. Spring bin name equals until successful store. Class equals com.prancingdonkey.objectstore.a cache object store. pcache ref equals until successful A cache. /spring beans. VM connector name equals VM connector. VMQ profile. QStore ref equals VMQ store. /VMQ profile. /VM connector. Flow name equals idempotent bridge. VM inbound endpoint path equals ib.in. Idempotent message filter. Spring object store ref equals idempotent store. /idempotent message filter. Until successful object store ref equals until successful store. Outbound endpoint ref equals proxied service. /until successful. /flow. Mule's internal persistence mechanism no longer has any secrets for you. Indeed, you should now be able to configure Mule's persistence to fit your needs and constraints. Clustering for E. The Enterprise Edition of Mule provides a clustered object store that can be used to perform distributed deployments of Mule applications and have their state transparently shared across a cluster. In this section, we've reviewed how using Mule's internal API can allow you to use lifecycle events, intercept messages, and listen to notifications in order to implement advanced behavior in your applications. You've also learned how to configure and customize Mule's data persistence. Now you're at the tipping point of your learning journey. You've learned a lot about how to build applications with Mule, from the simplest to the most complex ones. It's now time to address the crucial point of testing. How can you test all this great stuff that you're building with Mule? Read on to find out. 12.4. Testing with Mule. Mule provides rich facilities to test your integration projects. We'll start off by seeing how to use Mule's functional testing capabilities to perform integration tests of your Mule configurations. We'll then take advantage of Mule's test namespace to use the test component to stub out component behavior. We'll wrap up by taking a look at Jmter, an open-source load testing tool, to load test Mule endpoints. 12.4.1. Functional testing. One way to perform integration testing on a Mule project is to manually start a Mule instance, send some messages to the endpoint in question, and do some manual verification that it worked. During development, this can be an effective technique to explore potential configurations. This process should ultimately be automated, allowing you to automatically verify the correctness of your projects. The functional test case of Mule's Test Compatibility Kit (TCK) can be used for this purpose. The TCK can be used to test various aspects of Mule projects. The functional test case allows you to bootstrap a Mule instance from a test case and then use the Mule client to interact with it. To demonstrate Mule's functional testing capabilities, let's start with a simple flow used by Prancing Donkey to asynchronously transform XML messages from one format to another. The configuration in listing 12.21 shows this flow, which accepts a JMS message off a queue, processes it with an XSLT transformer, and then sends it to another JMS queue. Listing 12.21. A flow used to asynchronously transform XML messages. You want to be able to test this flow independently of any JMS provider. This means that you'll have to configure the Mule application differently for functional tests and deployment. This is achieved by externalizing the connector's configuration in a separate file and having two versions of this file, one for tests and one for deployment. The flows will be in another file, which will remain the same for all environments. When running functional tests, you'll then need to start a JMS provider before the tests start, and stop it after they're done. For this you'll use an in-memory, non-persistent JMS provider, as shown in the next listing. Listing 12.22. A connector's configuration file used during functional tests. This configuration is fairly straightforward. One thing to note is the use of the ActiveMQ connector. By default, this creates an in-memory ActiveMQ broker that lives for the duration of the functional test. In-memory infrastructure providers. Use in-memory Java providers to test endpoints that typically require enterprise infrastructure like JMS, JDBC, SMTP, or POP3/IMAP. Popular options include ActiveMQ's in-memory transient, non-persistent, broker, Apache Derby or HSQL in-memory databases, and Greenmail in-memory mail server. Let's write a functional test for this configuration. The goal is to start Mule, send a JMS message to the messages.v1 queue, and then consume a message off the messages.v2 queue and confirm that the transformed payload is present. Use the functional test case along with the Mule client to get this done, as illustrated in the following listing. Listing 12.23. A functional test case that exercises a flow with JMS endpoints. You start off by specifying the locations of the Mule configuration files. Load side-by-side functional test connectors.xml, which contains the in-memory JMS connector, and JMS transforming bridge.xml, which contains the flow to be tested. Typically the test configuration files would be located in src/test/resources and the deployable files in src/main/app or src/main/resources, depending on the deployment you target. See Chapter 8. The test method is annotated with a standard Unit 4 at test annotation. In it, you get the Mule client from the Mule context present in the org.mule.tck.unit4.functional-test-case superclass. You're sending a JMS message to a one-way endpoint, so you don't expect a synchronous response, hence the use of the dispatch method of Mule client to send a test payload to the messages.v1 queue. The message will now be sent to the in-memory ActiveMQ broker configured in listing 12.22. You request a message off of the JMS messages.v2 queue with a timeout equal to the maximum possible timeout for a functional test. 10. Use the maximum possible timeout because there's no way to know beforehand what could be a reasonable wait time. Using a too small timeout can lead to a test that is intermittently failing, something that can be tricky to figure out. In practice, this timeout will never be reached, and the rest of the test will be executed as soon as a message arrives in the messages.v2 queue. 10. The default value is 60 seconds. This is configurable via the mule.test.timeoutSex Java system property. Assuming everything went well, the transformed message with transformed payload should be waiting for you patiently on the messages.v2 queue. If you don't receive a message off the queue in that time frame, the test will fail. Assuming a message has been received, You perform your test assertion and ensure the payload has been transformed appropriately. Transformer testing. The org.mule.transformer.abstract transformer test case can simplify and speed up transformer testing. Listing 12.23 used Mule to dispatch a test message over JMS. This is convenient, but has the drawback that Mule is used on both sides of the test. It's good practice to write tests that resemble real use cases. This means that if Mule isn't involved in the client side of the real use case, it's better not to use it as a client in tests. There are numerous Java libraries that can help you with that. For example, the Apache HTTP client, hc.apache.org web link, would be perfect for testing HTTP endpoints. What about JMS? Let's rewrite the preceding test without Mule as client and find out. Listing 12.24. Using pure JMS to test a flow with inbound and outbound JMS endpoints. Listing 12.24 shows the test rewritten using standard JMS client code to interact with the JMS provider to which Mule is connected when the test is run. As you can see, the code is more involved than when Mule is used to produce and consume the source and result messages, which says a lot about the heavy lifting Mule is doing behind the scenes. In practice, you'd most likely share this JMS code in a utilities class or use a ready-made client, like Spring's JMS template. The functional test case is capable of great things but is complete when it's working with its sidekick, the functional test component. Let's learn more about it. 12.4.2. Behavior stubbing. Another important item in your Mule testing toolbox is a component that manifests itself as the test component, configuration element and the functional test component class. This component allows you to log details about the message it processes, set the current message payload to a configured string value or the content of a file, append a string to the payload of the message it processes, slow down a flow execution by making the current thread sleep for a while, break the flow execution by throwing a configured exception, capture messages that flow through it, invoke a custom callback when it receives a message. You can use the functional test component in any flow you like. Because it's preferable to use the same flows in test and deployments, you likely won't use this component in flows that end up deployed in production. Where this component truly shines is for stubbing out the behavior of external systems that your flows interact with. Let's see how. Test in production. If you end up shipping flows that contain the test component in production configuration, prevent its execution by wrapping it with a choice router or a filter router. Then use a message property to flag test grade messages that will be the only ones allowed to hit the test component. Let's functionally test an integration flow that you've seen before. Listing 12.25 comes straight from section 2.2.3. As you can see, this flow interacts with a remote web service over HTTP. How can you test this without calling this remote service? Listing 12.25. A flow that interacts with a remote service. Flow name equals Acme API bridge. VM inbound endpoint path equals invoke Acme ME. JDBC outbound endpoint query key equals store data. HTTP outbound endpoint address equals acme.com web link. /flow. You start by externalizing the endpoint definition in its own configuration file, turning it into a global endpoint, and referring to it from the flow. That's what you see in the next listing. Listing 12.26. A flow that interacts with a remote service via a global endpoint. Flow name equals Acme API bridge. VM inbound endpoint path equals invoke Acme ME. JDBC outbound endpoint query key equals store data. HTTP outbound endpoint ref equals Acme API endpoint. /flow. Notice how the HTTP outbound endpoint now references a global endpoint named Acme API endpoint. With this in place, you can now create a test configuration file that contains a global HTTP endpoint named Acme API endpoint, but that doesn't interact at all with a remote service. You'll provide a stub of the remote service in the same test configuration file, using a standard flow to implement it. This flow will use the functional test component to simulate the remote service behavior, including potential failures, and, more generally, instrument the service stub. The following listing shows this test configuration file. Listing 12.27. A test configuration file within memory transports and service stubs. Spring Beans. Spring JDBC embedded database id equals JDBC data source type equals HSQL. Spring JDBC script location equals class path test ddl.sql. /Spring JDBC embedded database. /Spring Beans. HTTP endpoint name equals Acme API endpoint. Address equals localhost $port, web link. Exchange pattern equals request response. Flow name equals Acme API stub. Inbound endpoint ref equals Acme API endpoint. Object to string transformer. Test component. Test return data result, success/test return data. /test component. /flow. Notice that, following the advice in the previous section, you use an in-memory database, HSQL, aka HyperSQL, to support the testing of this flow, which also interacts with a JDBC endpoint. You don't need to provide a global endpoint here because the connection factory is the natural seam you use to replace the database with an in-memory one during testing. You're most likely wondering where the $port value comes from. Hold tight, we'll look into this in a second. The way you use this test configuration file is similar to what was discussed in the previous section. You'll load it side by side with the configuration containing the deployable flow. This means you'll load functional test stubs.xml and Acme API bridge.xml in your functional test case, shown in the following listing. Listing 12.28. A functional test that uses a stub.http service. Notice how you receive a port by injection? That's how the $port value gets generated and how you could use it in your test, if needed. Mule will look for an available port, in the 5000 to 6000 range, and will assign it to your test. Should you want to interact with the open port from your code, you could call port.getNumber to find out what value has been assigned. You can have as many dynamic ports as you need and use whatever field names you want, as long as each of them is annotated with that rule. This is extremely convenient for running functional tests on a continuous integration server without messing with other tests or with the host server itself. Dynamic ports rule. Use dynamic ports in functional test cases to make them play well on developers' workstations and continuous integration servers. Why the call to thread.sleep? The reason is that without it, your assertions would run before anything has been dispatched by Mule. Why is that? Look again at the flow you're testing. Its message source is a VM inbound endpoint, which is one way by definition. This means that after dispatching the test message to the VM endpoint, the execution will immediately proceed to the next step, exposing you to the likely scenario in which you would run assertions while Mule is, behind the scenes, still routing the message. Using thread.sleep to wait for the messages to have been dispatched is naive because there's no way to figure out a sleep time that will work well in all circumstances. Make it too short, and it won't wait long enough on a busy continuous integration server. Make it too long, and running the tests on a developer's workstation would be excruciating. Let's fix that now. You'll use a latch to hold the test execution until the dispatched message hits the functional test component in the remote service stub. For this, you'll instrument the functional test component with an event callback that will release the latch. The code in next listing shows the test method now relieved of its naive thread.sleep. Listing 12.29. A latch suspends the test execution until a message is received. Await, don't sleep. Avoid using thread.sleep in functional tests to wait for dispatch operations in Mule. Instead, use event listeners and concurrency primitives to control the test execution. You could decide to test your flow to ensure it behaves correctly if the remote service returns an error. For this, you could configure the functional test component differently in another stubbing configuration file, as shown in the next listing. Listing 12.30. Using the test component to simulate exceptions. Test component throw exception equals true. Exception to throw equals java.lang.runtime exception. You could also test your flow's behavior in case of slowness from the remote service by using again a specific feature of the functional test component, shown in the next listing. Listing 12.31. Using the test component to simulate slowness. Test component wait time equals 15,000. Test return data result, success/test return data. /test component. By now you should be comfortable writing functional tests with Mule and mocking component behavior using the test component. You'll now see how you can perform load tests on a running Mule instance. 12.4.3. Load testing. Extensive functional tests coupled with automated integration testing should provide you with a fair bit of reassurance that your Mule projects will run correctly when deployed. The real world, however, might have different plans. Perhaps Prancing Donkey's asynchronous message transformation service shown in listing 12.21 will have to deal with unexpected peak loads during Black Friday. Unaware of the demand for such a simple service, you deployed Mule on a spare blade server loaned to you by a colleague in operations. Mule performs admirably on this blade, easily processing 100 or so messages every minute. Suddenly, however, you notice the service is crawling, and the load on your lowly spare blade server is through the roof. You check with Prancing Donkey's JMS administrator and realize that thousands of messages are being sent to the messages.v1 queue every minute. Deciding it's time to gain deployment flexibility, you deploy Mule to the cloud, automatically provisioning Mule instances to consume messages when the message volume becomes too high. To do this, however, you need to determine how many messages the transformation service deployed on a single Mule instance can handle. Apache Jmter is an open-source Java load generation tool that can be used for this purpose. Jmter allows you to generate different sorts of load for a variety of services, including JMS, HTTP, JDBC, and LDAP. You can use these facilities to load test Mule endpoints that use these transports. In this section, you'll see how to use Jmter with JMS as you load test the service you performed integration testing on previously. To start off, you'll need to download Jmter from jmter.apache.org web link. The example in this section will test JMS, so you need to provide your JMS provider's client libraries to Jmter before you start it up. This can be done by copying the appropriate jar files to the lib/subdirectory in the root of the Jmter distribution. 11. Once this is done, you can start Jmter from the bin/subdirectory, either by double-clicking on the Jmter jar file or by running the appropriate shell script for your platform. If all of this went correctly, you should see a screen resembling figure 12.8. 11. Prancing Donkey uses ActiveMQ. So we dropped ActiveMcall 5.6.0.jar in the lib/directory. Figure 12.8. Starting Jmter for the first time. Start by specifying a test plan for a load test. Do this by right-clicking on the test plan icon, selecting Add, and then selecting Thread Group. The thread group is what you'll use to control the amount and concurrency of the JMS messages you'll send and receive. After talking to Prancing Donkey's JMS administrator a bit more, you manage to nail down the load problems starting to occur with 5 concurrent producers sending about 20 messages each and a similar number of consumers. You figure this is as good a baseline as any to begin your load testing experiments, so you set their values in Jmter, as illustrated in Figure 12.9. Figure 12.9. specifying a thread group to simulate 5 concurrent JMS producers sending 20 messages. Set the name and, if you want any, comments. You want your tests to continue if there are any errors along the way. This could allow you to detect and debug failures in the JMS infrastructure itself, for example. Selecting Stop Thread here will cause the thread that encountered the error to exit and not send any more messages. Stop Test would cause the entire test to stop when an error is encountered in any thread. The number of threads, users is then set to 5. The ramp-up period indicates the amount of time to delay starting each thread. In this case, you want all 5 threads to start at the same time, so you set the value to 0. The loop count indicates the number of messages you want each thread to send. In this case, you want each user to send 20 messages, and then stop. Clicking Forever here will cause each user to send messages indefinitely. You now need to add a JMS sampler to the load test. In Jupyter, a sampler is responsible for generating the traffic used for the test. Set up a JMS sampler by right-clicking on JMS test, selecting Add, selecting Sampler, and then selecting Publisher. The Publisher sampler indicates that you want to generate data for a JMS queue. This should lead to a screen that allows you to configure the details of your JMS broker and specify the messages.v1 queue as the destination for the test messages. Figure 12.10 illustrates the configuration for Prancing Donkey's staging ActiveMQ broker. Figure 12.10. Configuring a JMS publisher sampler with Jupyter. Similarly, you need to configure a JMS subscriber sampler to consume the transformed messages that have been sent to the messages.v2 queue. Figure 12.11 shows this configuration screen. 12. You don't add any particular assertion to check the content of the transformed messages because you already test this behavior with function tests, and you don't expect to receive garbled messages even under load. It's all or nothing with JMS. If you had a doubt about potential corruption under load, you would need to add an XML assertion node to your Jupyter test plan. 12. ActiveMQ binds dynamic queues in JNDI under the dynamic queues/root. Figure 12.11. Configuring a JMS subscriber sampler with Jupyter. With this in place, you're almost ready to start your load test. You could start the test now, but you'll want to collect some data as you run the tests. This is accomplished by adding listeners to the thread group. Right-click on the thread group, select Add, select Listener, and select a listener you'd like to use to interpret the test results. For this case, let's add the aggregate graph listener. You can now run the test and view the results. Click on the Run menu and select Start. You should see a green light on the upper right-hand side of the screen as the test runs. 13. If your test fails to run, or if any failures occur during it, you can view them in the jupyter.log file located in the bin subdirectory you use to launch Jupyter. If you click on any of the listeners as the test is running, you should see the results being populated. This should resemble Figure 12.12. Figure 12.12. Examining results of a Jupyter listener. The listener results will be appended as subsequent tests are run. This will allow you to trend things like throughput as you increase the load of your tests. You can now use this test to load test the message transformer on the Mule instance. By examining the message throughput as you increase the number of threads and messages they send, you should be able to identify the point at which performance begins to drop off. You can then use the techniques you learned about in Chapter 11 to try to squeeze more performance out of the Mule instance. Ultimately, you should be able to get a good idea of how many messages the given Mule instance on the given platform can handle, allowing you to make intelligent scaling decisions. We've only scratched the surface of the capabilities of Jupyter. As mentioned in the introduction, Jupyter can test transports other than JMS, like HTTP or even plain TCP. You can even implement your own samplers if there isn't a pre-supplied one for the endpoint you wish to test. Test automation is also available, allowing you to integrate load tests into your build processes or IDE. Full documentation is available from the JMTR site, jmtr.apache.org web link. By now you should be comfortable testing your Mule projects. You saw how Mule's Test Compatibility Kit facilitates functional testing of your components, transformers, and Mule configurations. You then saw how JMTR, an open-source load testing framework, can be used to load test your Mule endpoints. As you'll see by developing your Mule applications, the need to grasp what's happening inside Mule at runtime will become more present. This is when debugging will become necessary. Let's now look at this final aspect of developing with Mule. 12.5. Debugging with Mule. Sometimes things don't happen as you expected, a flow doesn't behave the way you initially designed it to. How do you find out why? Or you may need to know all the specific message properties a transport has created on the messages it gives to your flows, because they're not fully documented online. Where can you look to find them? If you're asking yourself these questions, it's time for you to learn a few debugging techniques with Mule. Enterprise debugging. The Enterprise edition of Mule comes complete with an advanced console, the Mule Management Console, MMC, which provides, among other things, a set of tools that can be used for debugging, like the Flow Analyzer. Mule being beyond the scope of this book, we'll focus exclusively on what you can do with the Community Edition of Mule and open source tools. The Mule Studio Visual Debugger, see the note Visual Flow Debugger, is a convenient tool for inspecting messages that flow through a Mule application running in this IDE. The techniques described in this section are applicable even if the Mule application runs on the standalone broker. They also allow you to get closer to the Mule code if the issue you're investigating can't be resolved by the surface-level inspection provided by the Visual Debugger. Visual Flow Debugger. Since version 3.4, Mule Studio offers a visual debugger that allows step debugging of the execution of flows, with each step being each message processor in the flow. This debugger, shown in Figure 12.13, supports conditional breakpoints and allows a deep inspection of the in-flight message. As of this writing, it's not possible to visually debug a flow started from a functional test. Figure 12.13. The Mule Studio Visual Debugger. The first technique we'll look at is as unsophisticated as the good old print statements you use to add to trace your program's execution. Don't deny it, we've all done it. 12.5.1. Logging messages. Logging messages is a simple and effective manner to gain good insight into what's happening in a Mule application. To circle back to one of the questions raised at the beginning of this section, listing 12.32 shows how you would log all the message meta information, properties, payload type, exception payload, of messages received by the HTTP endpoint in your flow. Listing 12.32. A flow that logs all message meta information. Flow name equals beers service. HTTP inbound endpoint address equals localhost : $port, web link. Exchange pattern equals request response. Logger level equals info. Exclamation mark, snip dash. / flow. By default, the logger message processor outputs all the message meta information at the configured log level. Refer to section 8.1.3 for more information about logging configuration. When an HTTP GET request hits the flow in the previous listing, the log output will look like the following. 12:42:25,124 info-connector.http.mule.default.receiver.o2 org.mule.api.processor.logger message processor org.mule.default message. Id equals 45 DAC 564 1 AE 11 E2 84 Ca 4 D33 FEC 1 Ed 8D. Payload equals java.lang.string. Correlation id equals not set. Correlation group equals 1. Correlation sch equals 1. Encoding equals u.t.f. 8. Exception payload equals not set. Message properties. Invocation scoped properties. Inbound scoped properties. Connection equals false. Host equals localhost :5281. Keep alive equals false. Mule _originating _endpoint equals endpoint.http://localhost.5281.api.beers. Mule _remote _client _address equals /127.0.0.1 to 45,782. User agent equals Jakarta Commons HTTP client /3.1. http://context.path equals /a.p.i/beers. http://context.uri equals localhost :5281 web link. http://headers equals host equals localhost :5281. User agent equals Jakarta Commons HTTP client /3.1. Keep alive equals false. Connection equals false. http://method equals get. http://query.params equals. http://query.string equals. http://relative.path equals. http://request equals /a.p.i/beers. http://request.path equals /a.p.i/beers. http://version equals http://1.1. Outbound scoped properties. Mule _encoding equals u.t.f. 8. Session scoped properties. Notice how the properties scopes are clearly represented. With this information in hand, you can start doing smart things based on the message properties, like routing messages that have a specific http://context.path inbound message property to a specific message processor with a choice router. As you can also see, the full payload is not logged. This is a smart default behavior. Some payloads can be big or confidential, so logging them could be an issue. Moreover, if the payload is an instance of a java.io.input stream, as is the case for HTTP POST requests, logging the payload would require deserializing the stream, preventing downstream message processors from working in a streaming manner. Target category. By default, the logger message processor logs under the org.mule.api.processor.logger message processor category. You can change that to any value you want by using the category attribute of the logger XML element. But what if you need to log the payload? The best way to do so is to use mel to log the payload rendered as a string. Mule will use its auto-transformation capacity, discussed in section 4.3.6, to find the best transformers for rendering the payload as a string. If the payload is streaming, it will be replaced by a deserialized form, for example, byte. The following configuration snippet shows how to configure the logger message processor to log the current message payload. And yes, if you want to log both the payload and the meta information, you'll have to use two loggers. Logger message equals #message.payload as java.lang.string. Level equals info. Logging message payload and meta information will help you to gain insight into what's happening within your flows. Sometimes, a finer-grained approach to troubleshooting is needed. This is when step debugging comes in handy. 12.5.2. Step debugging a Mule application. Step debugging in Mule is easy to set up but can be hard to use, and this is because of the long chains of class extensions on which most moving parts rely. Said differently, if you place a breakpoint in a generic abstract class used by many moving parts of Mule, you'll end up breaking the execution constantly without clearly knowing where you stand. Another complication with step debugging in Mule comes from its heavily multi-threaded nature. The execution may at some point in time escape your step debugging session because it's been handed off to a different thread. Without further ado, let's start step debugging a Mule application. This is initiated differently depending on the way you're running Mule. inside your IDE. In this case, start in debug mode using your IDE-specific command. This applies to Mule Studio as well. Deployed in a web container, for this situation, refer to the Remote Debugging section of your Web Containers User Guide. Using the standalone distribution, enable remote debugging by adding the debug parameter to the start command. Stack traces, longer, deeper, chattier. By default, Mule shortens stack traces logged when exceptions occur. If you want to go for the full Monty, start Mule with the mule.verbose.exceptions system property set to true. With Mule standalone, this is done by adding a m-prefixed parameter to the start command. /bin/mule and mule.verbose.exceptions equals true. For this discussion, we'll consider remote step debugging Mule standalone with Eclipse IDE. When started with the debug parameter, Mule standalone listens for remote debugging connections on port 5005. Figure 12.14 shows how to connect Eclipse to Mule by creating a remote debug configuration. Figure 12.14. Connecting Eclipse to Mule standalone for remote debugging. In order to step debug in Mule's code, you need to have the Mule source code available to Eclipse. If your project is built with Maven, the Mule source code is most likely attached to your Eclipse project already. Otherwise, you can find it in the /src/muleaction00122 archive provided with the Mule standalone distribution. We've previously warned you about placing breakpoints in counterproductive locations, so what are good places for breakpoints? The following list should give you an idea. Terminal Mu moving parts, classes that are at the bottom of class hierarchies, such as transformers. Pojo components, your own classes that are used as flow components. Custom message processors, your own custom implementations, including specific interceptors. One powerful debugging tool to consider is conditional breakpoints. Consider the case where you have multiple first successful routing message processors, discussed in section 5.5.1, used in several flows, and you want to suspend the execution only when one of them gets used in a particular flow. This is when you'll need a conditional breakpoint. Figure 12.15 shows you how to set a breakpoint in the source code of org.mule.routing.first successful that will be triggered only when it's used in a flow named order delivery flow. Figure 12.15. Setting a conditional breakpoint in a generic Mule class. Get out of my script. Scripted components and transformers are convenient, but be aware that you won't be able to put breakpoints in the scripts, and this is true for whatever scripting language you use, Mel, Groovy, or any other one supported by Mule. This warning should serve as a reminder that scripts must be kept short. If your scripts turn into classes in disguise, rewrite them as Java classes and unit test them properly. The added bonus will be the ability to step debug them. Conditional breakpoints are the way to go when you want to suspend execution in Mule classes that are used over and over. With the debugging tools we've covered in this section in hand, you should be able to gain a deep insight into what's happening when Mule runs your applications. 12.6. Summary. The Mule API is a rich and comprehensive gateway to all moving parts of the ESB. Though using the API creates coupling between your code and Mule itself, we've explored a wealth of scenarios in which the drawbacks of such a coupling are overcome by its benefits. You saw in this chapter how it's possible to use this API to perform actions of all kinds, including exploring the inner parts its context gives access to, communicating with a running Mule instance, intercepting messages, and listening to internal events. You also learned how to customize Mule's own data persistence. Finally, you discovered how to test Mule applications, from both functional and performance standpoints, and how to debug them. We haven't covered using the Mule API for creating new connectors, and this is for a reason. Mule offers a specific code generation tool, DevKit, that allows for the creation of new connectors by writing annotated bojos. This is what we'll cover in the next chapter.